section 4.7 today on applied optimization problems. And these problems are sort of the natural applications that fall out from these maximum and minimum problems that we've been working on for the past few sections. There are lots of reasons why we might want to find the max or min of a function. Like if you own a business, you may want to figure out how many advertising dollars you should spend in order to maximize your profit. Or maybe you're designing a product and you want to figure out the shape of this product so that you're going to minimize the amount of material or the amount of cost it would take to produce your product. So there's lots of reasons why we want to find these maximums and minimums, and calculus is really well designed to do this because of the critical points that the derivative gives us. All right, so we're going to start off with a pretty simple example. We are going to be looking at building a rectangular pen for our favorite goat. All right, so I have this Desmos file linked on our resources for the week if you kind of want to play along. And we have a couple of caveats to this goat pen problem here. And the first one is that we've already bought all of our fencing. So we have 2,400 feet of fencing that we can use to build this rectangular pen for our goat. And this is our favorite goat. We love our goat. And so we're going to try to build the fence in a shape so that this goat has as much room to roam around on as possible. And so to that end, we have a river on our property. All right, so we're going to build this rectangular pen up against the river. So ostensibly, the river can be the fourth side of our rectangular pen. I have no idea if the goat is going to try to swim, but we'll just pretend that he's going to stay inside his pen, bound by the river. All right, so you can turn on the pen, and it's got a draggable point on the side. So you can kind of choose the shape that you want to. So I'm going to choose my shape by dragging that corner point around. All right, and it's got it constrained for those 2,400 feet of fencing. It's only if you pull it really, really wide, it's going to force you to make it really, really short because you're using up a lot of fencing for the width, so you don't have much left over for the height. So likewise, if I want to make it really skinny, I can do that. I have more fencing to use for the height this time. All right, so if you turn on the labels, let's pick something a little more reasonable here. If we turn on the labels, it's going to tell you what the width and the height is, and then the corresponding area, which is really what we're trying to maximize, the square footage that our goat has. So any point you want to check, 2 values of the height plus 1 value of the width is going to equal 2,400 feet. And then it gives you the corresponding height times width for the area in the middle. And you can kind of play around. When I'm out here, I've got 600 something thousand square feet. I get into the 700s up here. And then after a while, we go back down into the 600s. So somewhere in here, these 700,000 range is going to be our optimal dimensions. So we're going to use calculus rather than dragging the point around on Desmos to solve for what that optimal spot is. So here I've recreated our Desmos file picture, sort of. We got a rectangular pen with the dimensions labeled H and W, and I took note of the fact that we have 2,400 feet of fencing to build this pen with. And we know we want to give our goat the most area to roam around in, and so we're going to say that we want to maximize area. So we're going to maximize area. And it's important to note the quantity that you want to maximize or minimize because that's the thing you need a function for. That's the thing you want to be able to take the derivative of. So I want to be able to come up with a formula for area. And we have an easy formula for area. We usually think of that as length times width. In this case, that's going to be H times W. And the trouble here is that I don't know how to take the derivative of a formula that's got 2 variables in it, right? That H and W can be anything that they want to be. Well, they can sort of be anything that they want to be. Once I picked that H, the W is kind of predetermined, right? Because of that constraint of only having 2,400 feet of fencing. So once I pick one variable, the other one is determined by that 2,400 feet. So we're going to get this area formula down to one variable so that we can handle it with a derivative by using that extra piece of information. So I have that 2,400 feet. So up here to the left, I'm going to say that 2,400 feet. Let's see, that's going to be 2 H sides of the pen, but just 1 W side of the pen because we're counting on the river to be the 4th side. So I'm going to say the 2,400 is equal to 2 H's plus 1 W. And this extra piece of information we're going to use to get our area formula down to one variable. And it doesn't really matter which one. So I'm going to solve that 2,400 equation down there on the bottom left for one of the variables. And W is going to be the easier one to solve for. I'm just going to subtract 2H from both sides. And I get that W is equal to 2,400 minus 2H. All right, and that W is the same W that's in my formula. So this formula for W is going to come up here and take the place of that W there. And then we can use that to turn that area formula into something, a function of one variable. So I'm going to rewrite my area equation. abbreviate that as A, and I've got H times W, but now W is going to be 2400 minus 2H. And that's a pretty easy function to take the derivative of, especially if I simplify a little bit. So we're going to distribute that H through the parentheses. So A, I can even write this as A of H, like function notation, because I've got 2400 times H minus 2H squared. And that's a function of one variable. And I can easily find critical points for that function to find out where its maximum is, where the maximum area is, just by taking the derivative and setting it equal to 0. So let's go ahead and do that. So we're going to find critical points. We're going to find A prime of H. Let's see, derivative of 2400H is just going to be 2400. And then derivative of 2H squared will be 4H. And we're going to set that equal to 0. And again, we're finding critical points here. So let's add 4H to both sides. If I add 4H to both sides, I get 2400 equals 4H, and then we'll just divide off that 4. And I get that H is equal to 600. All right, so my H should be equal to 600. And that's going to be our answer. We're going to want this pen to be 600 feet tall. So we're going to use 600 feet over on the left, 600 feet over on the right. Let's see, that's 1,200 feet. And that means that we'll have 1,200 left over to be our width, right? So our pen is going to be 600 feet by 1,200 feet. And just to be specific, we'll say 1,200 feet along the river. All right, and that's going to be our answer. There's one last thing that we have to check, we need to be careful of, because a critical point, when you take the derivative and set it equal to 0, it might have given you the maximum spot, like we want, that maximum local maximum. It might have also given us a minimum. So we may have just accidentally minimized the amount of space our goat has to roam around. We haven't, but we do need to double check this, because this can happen when you're taking derivatives and finding critical points. All right, so we have one choice. We could make that increasing decreasing chart that we did back when we were graphing functions in section 4.5. There's actually an easier way to do this with what is called the second derivative test. All right, so I've recopied our function, the derivative, and the critical point value for us, and I'm going to explain to you how to use the second derivative test to tell whether or not you're looking at a maximum point or a minimum point. So we want to make sure that we've maximized the area, that we're looking at this kind of spot, and that we haven't accidentally minimized the area that our goat has to run around in. Now, in this particular problem, we could rely on our pre-calculus knowledge to say that area function is a downward opening parabola. It's got to be the first case where we're at a maximum point with our critical point, but our functions are not always going to be parabolas. So we really need to know how to use the second derivative test. So what the second derivative test does is it relies on concavity. So remember, the second derivative tells you whether you're concave down or concave up. So if you're sitting at a critical point and you're concave down, you must be sitting at a maximum. So that's actually what we want in this case. We want to see that we are concave down. And that's where our second derivative, in our case, a double prime, would be negative. If we had a minimum, then we would be concave up. And our second derivative would be positive. So all we need to do in these problems is double check to make sure that our second derivative is negative, that we actually have a maximum, that we're sitting at a concave down spot. So this is super easy to do. We're going to go over to our first derivative, take the second derivative, and see the 2400 gets wiped out by the second derivative, and we're left with -4. All right, so the second derivative of this function is equal to -4. It's actually a very boring function, right? Any point we plug into that second derivative, it's going to give us the answer of -4. So even if we ask it what the concavity is doing at exactly our critical point 600, it's still going to tell us -4, which is less than 0, which means we're in this concave down case, which means we found a maximum. So all we're going to do to double check and make sure that we got the right kind of critical point is to take the second derivative and examine concavity there. All right, so we've double checked to make sure that we actually found the maximum area by finding this 600 foot by 1,200 foot pen, and we've got our pen ready to go for our goat.